Okay, so the reason I put this question up is because I want to review a couple of things about energy first off. Okay, is energy a scalar or vector quantity? Like, have we ever written joules and then a direction? No, it's because energy is scalar, okay? And the reason I put this question up there is because sometimes people look at this and they say, well, if they jump out of a plane, that speed is horizontal. It has nothing to do with the speed at which they hit the ground. Now, the problem with that idea is that that's wrong, okay? Energy is scalar, okay? And it doesn't matter which direction that 90 meters per second is, it contributes to the person's kinetic and thus mechanical energy, right? Because people always envision when something hits the ground after having fallen for a long way, that it's moving only vertically. Is that true? No, it's moving horizontally as well. And technically, when we do a kinetic energy calculation, that V is not velocity. That V is speed. Okay, it doesn't have any direction. Okay, have I ever written the kinetic energy formula with an arrow over top of the V? Not once. I might once in a while occasionally use the wrong word in the question. I might use velocity just because I wasn't thinking. Okay, but it's always speed. Okay, the direction the person's going makes no difference whatsoever because energy is scalar. The ability of them to do work on the ground if they hit it, okay, is the same whether they're moving vertically or moving horizontally. Okay, they're going really fast and they want to open their parachute. Okay, everybody with me on that? Okay, so I just want to illustrate that because I find that it's not so much a problem in Science 10, but it becomes a problem in Physics 20 when we deal with a lot more vector stuff. We need to remember that energy is scalar. Okay, direction of the speed does not, well, speed doesn't have direction, but the direction the person is going does not matter. All right, so if we are solving this one, okay, we have a skydiver jumps out of the plane, okay, moving at 90 meters per second, so that'll be VI. Okay, their initial height is 10,000 meters. Okay, and we want to find out how fast they're going when they are 8,000 meters, okay, above ground level. All right, so we'll start it out, EI equals EF, okay? They're gonna have both kinds of energy at both points, so we'll have initial potential, initial kinetic, final potential, and final kinetic, okay? What we're looking for is part of final kinetic, so I'm gonna subtract the initial potential over to this side, so I'll have initial potential plus initial kinetic minus final potential equals final kinetic. Okay, then I can plug in my formulas, m times g times h initial plus 1/2 mv initial squared minus m times g times h final equals 1/2 mv final squared. What can I do with all the m's? Cancel them out. Okay, they never did tell me the mass of the skydiver. All right, so guys, generally if a question doesn't give you the mass, you probably don't need it. Okay, it's pretty rare that I would forget to put it in a question if it was something you needed. Okay, all right, so we're looking for VF, so we divide both sides by 1/2. So it's basically the same thing we did in our quiz a few minutes ago, and then we square root. All right, so when we're plugging in our numbers here, we are going to have some big numbers. Okay, 9.81 times 10,000 plus 1/2 times 90 squared minus 9.81 times 8,000 divided by 1/2. That's really fast. Okay, really fast, 217. Okay, but it is possible for someone to go faster than that while falling. Okay, what was his name? Baumgartner there, the guy that jumped from like low Earth orbit. Okay, was actually going faster than the speed of sound in a couple of points during his fall. Okay, so You can definitely go faster than that, but you wouldn't want to go too much faster than that. The only reason he was able to survive going faster than sound was he was in a very thin part of the atmosphere. The lower you go, the bigger the problem that will be. Is that? Yeah, he did. Yeah. All right. Is that making sense? Seems like we're getting these conservation of energy kind of questions. Okay. So rather than do a whole bunch more right now, I want to talk a little bit about the lab that we're going to do tomorrow. Okay, kind of how it relates to this stuff here. Okay, so just so we can kind of see what that's going to be like. Tomorrow, we're going to do a lab where we're going to convert gravitational potential energy into kinetic energy. Okay, it's very easy to do that. You put a cart on top of a ramp and you let it slide down the ramp. Okay, and that converts potential energy into kinetic energy, right? The issue is being able to measure everything that we need to measure in order to calculate the different kinds of energy, right? So here's our situation. We're going to have a ramp. We're going to have a cart at the top of the ramp. What are some things we'll be able to measure about the cart at the top of the ramp? Okay, we'll be able to calculate or measure its mass. Okay, so that'll be important. Okay, and its height, somebody said. All right, so we'll have that. Okay, is that really all we need at the top of the ramp? Yeah, because it's going to be stationary at the top of the ramp. We're going to release it, so it's only going to have potential energy at the top of the ramp. Now, bottom of the ramp, okay, we're going to need to know, again, its mass, which we'll have already measured, because we'll just put it on a scale, or I'll just tell you. Okay, and what else? Speed. How am I going to measure that? Problem is that it's accelerating down the ramp. It's not traveling at a constant speed down the ramp. So we can't, I mean, if we had some other formulas, we might be able to do that, but it's not going to be very easy because it goes down the ramp very quickly, right? It's hard to measure accurately time and things like that. So what we're going to do instead is we're going to combine a little bit of conservation of energy with work energy theorem. We're going to let the cart go right off the end of the ramp. Okay, we're only going to be concerned with the energy between the top of the ramp and the bottom of the ramp, but we're going to see how far it goes on the level floor. Because what's going to bring it to a stop on the floor? Right, loss of energy due to friction. Okay, now we can measure along the floor how far it goes. That was one of the things we wanted to know. Okay, and we can measure also how long it takes for it to come to a stop. So we'll have time. Okay, we'll know its final velocity. Agreed? Its final velocity will be what? 0, because it's going to come to a stop. Okay, so we're going to be able to calculate, essentially, using work energy theorem, how much work is done to stop the cart. Now, if we can calculate how much work is done to stop the cart, is that equal to the energy it has at the bottom of the ramp? It is. All right, so we're going to have to do a little bit of measuring, okay, but we're going to be able to do it. We're going to have to use a formula that you'll only use in this lab. You'll never be asked to use it again in Science 10, but it's like the first acceleration formula we use in Physics 20, okay? So what we'll be using is 2d over t squared equals acceleration, okay? We'll be using that formula. You don't have to remember that formula. It's going to be on the lab, okay? But we're going to use that to calculate the acceleration. Okay, we'll have the mass of the cart, so we'll be able to go mass times acceleration, and that'll get us force. Okay, which force is stopping the cart? Friction. Okay, if I take that force and I've measured how far the cart travels, can I calculate the work done in stopping the cart? Okay, so that's what we're going to do, because timing and measuring the cart as it slowly, and it does slowly come to a stop, is way easier than trying to reaction time something going down a ramp. Okay, we could do it, but we wouldn't get very accurate data. So it's way easier to measure the cart as it's very slowly coming to a stop due to friction after it leaves the ramp. Everyone with me on that? Okay, it actually eliminates a bit of reaction time error because we don't have to start timing it until it gets to where? right to the bottom. So we can anticipate that. We can watch it go down the ramp, start the timer as it gets to the bottom of the ramp, and then watching it slow down, slow down, slow down. Like it's not going to be a major reaction time thing to stop the watch on time as it slowly comes to a stop. So we'll be able to measure more accurately that part of the movement than we could the part of the movement we're most concerned with. Okay, so once we have the amount of work done, okay, we're saying that that's going to equal the kinetic energy that it had at the bottom of the ramp. Okay, once we have that, we can compare it to the potential energy it had at the top. Okay, so we're kind of bringing in all of the energy stuff that we've talked about in this unit into this lab. Okay, we're going to have to calculate potential energy, m times g times h. That's easy. Okay, we're going to have to calculate kinetic energy. We're doing that in a roundabout way, but you'll have all those formulas, and I'll go over that again tomorrow. Okay, really all we have to do is accurately measure distance and time for the cart as it rolls off the ramp. Okay, that's really the only thing we have to make sure we accurately measure. Okay, now, in the perfect physical world, what should the relationship be between this and this? They should be the same. Are they going to be? No. Okay. How much energy do you suppose a cart loses between the top of the ramp and the bottom of the ramp? It seems like that should be pretty simple, right? I mean, it's just sliding down a ramp, right? It's usually between 50 and 70%. Okay? It's incredibly inefficient. Okay? Even converting something as simple as potential into kinetic, okay, seems like that should be a pretty simple conversion. It ends up being not very simple at all and not very efficient. Okay, now granted it's a cart with wheel bearings and things like that. It's going down a wooden ramp that's got grooves carved in it so that it can't fall off the ramp. It kind of keeps it in the ramp, which means it hits the sides and stuff like that. So it's it's not as simple as just sliding something down a frictionless surface, because we don't have any frictionless surfaces. And what we want to get out of this lab is obviously the review of work energy theorem and conservation of energy, but we also want to look at the consequences of energy conversions. Okay, every time we convert energy from one form to another in the real world, energy is going to be lost. Okay, now it's not destroyed, it's just turned into forms of energy that are not useful. What's the most common form of non-useful energy? Heat. Sound would be second. Okay, and sound usually goes along with heat because it's usually due to friction. All right, so we're definitely going to lose some energy there. So what we have to consider is when we're looking at the ways that we power things and the ways that we use energy, okay, are they efficient? Are there more efficient ways to do things? Okay, because if we look at how we generate electricity in Alberta, okay, how do we generate electricity in Alberta? Coal. Yeah. Okay, even though they're trying to phase out coal, coal still represents close to 90% of our electrical generation. All right. I know that you go to Chinook Mall and they're like, we're wind powered. Well, so is this school. So is every place in Alberta by about 2% maybe. Okay, the Pincher Creek wind farms don't contribute very much to the overall Alberta power grid. Okay, most of our power is generated by coal. Okay, you can see there's a coal plant. If you go to North Calgary on Stony, you drive right past one. It's got the big steam coming out of it all the time. Okay, so coal generates electricity for the most part for us. Now, what that does is it takes coal, which is chemical energy, and it burns it, which turns it into what? Heat. Okay, so we turn chemical energy into heat. Now, what do we use that heat to do? To make steam. All right, so then we've got to convert steam, okay, from one form to another. All right, so that's essentially a thermal energy conversion, okay, of liquid water into steam. All right, so the steam has kinetic energy. What does the steam do? It turns a turbine, so that heat has to turn into mechanical energy. Okay, and what does the turbine do? Generates electricity. Okay, there a fair amount of energy conversions going on before we get to electricity? Yeah, there's quite a few. Okay, the more of those steps we can eliminate, the more efficient the energy conversion is going to get in general. All right, so if we're looking at like a wind-powered turbine, certainly that's converting the mechanical energy that turns the turbine into electricity more efficiently because it represents less steps. Okay, but there's obvious drawbacks to wind power. Okay, the first being, yeah, it's less controlled. There's always coal. Okay, we can always have the coal plant running. If it's not windy and you're entirely dependent on wind power, you don't have any electricity. Okay, the same is true for solar power. Okay, solar power is wonderful as long as there's enough solar energy hitting the solar panels. And when do we need energy the most? At night and in the winter. Okay, when do we have the least and lowest quality sunlight? At night and in the winter. Okay, so unless you can store it all up and still have it accessible to you, okay, during the times of the year where it's not efficient, okay, it's not going to be as reliable as fossil fuel generating electricity. That's why we use it. Okay, it's consistent, okay, and it's reliable. Is it efficient? No. Okay, is it non-polluting? No. Okay, but it's reliable, right? And there has to be some argument made for a reliable source of energy. Okay, and like guys, for solar power, this is the worst time of year right now to try and rely on solar power. I mean, if you ever watch, like, as you get older, like, just watch the sun. Don't look at it for too long because that's not good for your eyes. Okay, but in the wintertime, like this time of year, the sun rises like over here in the southeast. It makes this pathetic little arc, okay, and sets just over there, okay, in the southwest. In the summertime, it's the exact opposite. It traverses the entire sky. It's almost directly overhead, and it's overhead for like 16 hours, right? But right now, we're getting less than 8 hours of sunlight, and the sunlight we get is low angle, which means it's not very intense, which means it's not great for using to generate electricity, okay, if we're using solar panels, right? Can you still do it? Yes. Okay, they use it to run like traffic lights and stuff like that that aren't wired into the grid, okay, and it can charge the batteries enough. Usually they have to plug in a generator at some point just to charge them a little bit, but okay, the solar panels can usually do that. Is it going to be enough to power your house? No. Okay, I had a guy down the block from me. He put, I can't remember how many watts worth of solar on his roof. Okay, in the summertime, the province paid him. Okay, like his power bill in the summer was a negative number. He actually got money in the summertime. But in the wintertime, it's just like everybody else. Okay, it didn't generate enough to overcome what he was doing. Okay, what's that? It is, and he had an air conditioner. So, having an air conditioner, running an air conditioner, having solar power, I mean, he was kind of offsetting his impact, which was good. Cost a lot of money to put the solar up, but okay, in the end it was good. But in the wintertime, I mean, he was using way more than his solar panels, could generate. Okay, and that's it. I mean, they are fairly efficient. They're turning photoelectric, energy or photovoltaic stuff directly into electrical energy. It's less steps than this, so it's more efficient. Okay, so those are things to look at. Okay, the other thing you got to look at when you're trying to be more efficient is where your energy comes from. Okay, I don't know if we've talked about this or not, but okay, if you drive, let's say, like a hybrid car, okay, is a hybrid car easier on gas than its internal combustion only counterpart? Yeah, it is. Okay, it is, provided you drive a hybrid car in the way it was meant to be driven. Okay. Well, no, not just even that, but like a hybrid car is going to save you more money and be more efficient in stop and go traffic than it is on the highway. All right, because a hybrid car uses the electric motors when you are loading the car. That is when you use the most energy. That's accelerating. All right, so it's best in stop and go traffic. When you're on the highway and you're just cruising, you're not using the electric motors at all. Okay, it's just using the internal combustion engine. The electric motors don't kick in unless the engine is under load. They're there to help the internal combustion engine. That allows you to run a smaller internal combustion engine than you would if you only had the the internal combustion engine. So if you've got like a Toyota Prius, for example, okay, so the hybrid version would have like a 1.2 liter like 4-cylinder engine, very, very small, plus the electric motor. Okay, if you had just the internal combustion version of that, you would probably have to have like a 1.6 liter. Okay, so it'd be a bigger engine because it doesn't have the help of the electric motor. Right, so if you're just driving it on the highway, you're not really doing what you thought you were doing by getting an electric or a hybrid car, because you're not using that electric motor, right? You're just using the smaller, internal combustion engine. That sort of makes sense. Okay. The same is true for buying an electric car. Okay. If we buy an electric car in Alberta, we're not really saving the environment. Okay. Sure, your car is not directly burning fossil fuels to get you from A to B, but where's our energy coming from? Coal. So you plug in your car and the coal plant has to burn hotter. Okay, they're just going to use more coal. That's going to kick more CO2 into the atmosphere. So unless you've got a whole bunch of solar on the roof and your solar is going directly to charge your electric car, you're not really reducing your environmental footprint. So it's something to think about, okay, when you're thinking about, I'm going to spend the extra money to buy an electric car and be environmentally conscious. Think about where your energy comes from when you do that. Oh yeah, and we're not even getting into all the chemicals even that are in the batteries, right? The batteries don't last forever. They've got lots of harmful chemicals in them. Okay? And I'm not saying that that's worse than the tons of CO2 that a internal combustion engine would put into the atmosphere over the course of a car's lifetime. I'm sure that there's a pretty, reasonable balance between those two things, but CO2 can be taken out of the atmosphere by plants. Lithium and heavy metals have to go somewhere. Okay? Those don't break down, right? An electric car? Yeah, I mean, if you were in California, absolutely. Okay, they have a lot of solar power. They have a lot of wind power. So you could put solar panels on your roof, and theoretically, you'd be able to charge your car using just the power of the sun. Okay, and so yes, in that area, making that decision is doing what you think it's doing, which is reducing your environmental footprint. Here, it's not really reducing your environmental footprint. Probably, yeah. Okay. Now, I mean, you have to look at, an electric car is more efficient. It is. It's going to be more efficient than a gas-powered car. It just is. Electric motors are more efficient than internal combustion. There's less friction, there's less heat, all that kind of stuff. But what you have to consider is, when I plug it into the wall, how much does my power bill go up now? Right? I'm saving money on fuel, but electricity is expensive. Okay, like I recently got rid of an electric hot water tank because my power bill was ridiculous. So I went to a gas hot water tank. And yeah, my gas bill went up, but my electric bill went down a lot more than my gas bill went up. Okay, I'm like, okay, well, I'm not being as environmentally sound by having this gas powered thing in my house, but bottom line is it's cheaper. Right? It was saving me money. So that's the trade-off you got to think about when you're buying an electric car in Alberta is, okay, is it going to save me money? Because it's not going to save the environment. Not really, not here. Okay, so think about that. I mean, certainly, guys, yes, an electric motor is more efficient. There's absolutely no argument on that. An electric motor is way more efficient, which is why a Tesla, okay, can out-accelerate even the most, well, I think I saw it like racing the big Hemi Hellcat Challenger, right? And it wasn't even close. Okay, like 700 horsepower of pure testosterone, chest thumping internal combustion. Okay, supercharged, the whole works thing, just sucking fuel. You could watch the gas gauge do this. Okay, and the Tesla with the electric motors killed it. Okay, because electric motors are A, more efficient, and B, there's a traction control computer that doesn't allow the tires to spin. All of the power goes to the road. There's no waste. Okay, and so while you're faster, it certainly doesn't look nearly as cool. I mean, the back of your Challenger shrouded in tire smoke is awesome. Okay, it looks cool, but it's not nearly as efficient, okay, as the electric motor is. Oh yeah, you got slippage, you got the changing gears time. Yeah, exactly. There's all kinds of advantages to the electric motor. Okay, and it's only recently that that's really been effectively put into cars. Because 10 years ago, nobody wanted an electric car because they're slow and they looked silly and they were whatever, right? Okay, but now, okay, now it's much more feasible. They're a status symbol. They're more efficient. They're faster. Yeah, it's crazy. Yeah, and it's a van, but it's just because the electric motors and the computers they have running them, okay, do a better job of it. Okay, so is that sort of making some sense? So the other perspective here, guys, that we're looking at this from for the lab is efficiency. Okay, so efficiency, and you probably talked about this last year in science, okay, is really a percentage. It's your output, okay, your output work. So effectively, the work that the car effectively, or whatever the machine is, effectively does, divided by the input energy. So it'll come out to a decimal. So if it comes out to 0.85, how efficient is it? 85%. Okay, so efficiency is easy to calculate. So for our lab, we would take the kinetic energy at the bottom of the ramp, divide it by the potential energy at the top of the ramp, and we'll have the efficiency of the conversion from the top of the ramp to the bottom of the ramp. Okay, everybody with me on that? All right, I'm going to give you a 3-minute break. I'm going to get that lab set up in your Google Classroom, and then we'll pull out the Chromebooks and we'll do the pre-lab stuff today, and then you'll have all of tomorrow to do the lab and the rest of the report. Hopefully we won't have any homework then.